Hi, my name is Oskar Fader and I'm giving you this presentation about Maxon motor data and operating ranges. The goal is to give you useful information about how to read catalog data of Maxon motors. First, we start with the application. Essentially, for a given application, the motor is supposed to run at a certain speed and at a certain torque. In our standard diagram, we represent the speed as a function of torque. Now, one possibility is that the operation is at constant speed and constant torque, so this is represented by this green point. Another option could be that the motor has to run at a much higher speed, but maybe at a lower torque, or it is at standstill. It is maintaining a given position against, for example, gravity. Or another option is that the motor has to accelerate. And usually for acceleration you need a higher torque. So at the end, these are what's called the load operating points. In the first section, we would like to look at the limits of the motor. So essentially it's about how to select the right motor size for a given application. We start with looking at motor speed. We need a motor with a speed limit that is high enough to cover all the operation points. The maximum permissible speed corresponds to the upper limit of the operating range diagram. In our case, the operation point with the highest speed cannot be covered. One would need a different motor with a higher speed limit. However, if this high-speed operation point is not needed, the original motor is good enough. The speed limit of Maxon motors can be found in line 23 in the specification section or in the diagram. Next, we look at torque. Essentially, all the operation points can be condensed and summed up in a few key values. One of them is the average load torque, or root mean square load torque. Another one is the extreme operation point. That's usually at the end of acceleration where we have the highest torque and the maximum speed. And of course, another important key value is the time needed to do this acceleration, or the time needed to run the motor at this very high torque. So essentially, what we need is a motor that can produce the necessary torque, and it means the torque on average. So what we need is a motor with what's called a nominal torque, which is larger than what the load requires. And of course, we need a motor that can produce on short term the torque needed to accelerate. The nominal torque can be found in line 5 of the motor data. Essentially, it limits the continuous operating range. Nominal torque represents a temperature limit. Up to this torque, the motor can be loaded continuously without overheating. Higher torques are possible, but only a limited amount of time. So that's called short-term operation. Nominal torque is a characteristic parameter for a given motor type and for a given motor size. A remark about the maximum continuous torque, or nominal torque, and heat dissipation. Since the nominal torque is defined under standard condition, as soon as you have a better heat dissipation, for example by mounting the motor on a large metallic structure or by having airflow near the motor or cooling fins or whatever, then the continuous operating range actually extends to higher values, and it's quite easy to gain 30% in torque. So essentially the data that you find in the Maxon catalog are quite conservative, but you have to verify that your heat dissipation is really better than standard. As you can see from the diagram, there is a short-term operation, which essentially means it's possible to overload the motor, but only for a limited amount of time. And the big question here is, how long is short? It all depends, of course, on what kind of motor you have, on the motor size and the motor time. For each motor there is a time scale, and essentially the limitations comes from the winding temperature, or more precisely how fast the winding heats up. The natural time scale is therefore the thermal time constant of the winding. It can be found in line 19 of the motor specification. Typically, this time constant amounts to several seconds or up to half a minute for larger motors. Now, how to read this diagram? At torques up to about twice the nominal torque, overload can be quite long, 20 seconds for a small motor up to several minutes for large Maxon motors. At an overload of 3 times the nominal torque duration, however, is already quite short. It's shorter than this thermal time constant. The low torque in our case is about 2.5 times the nominal torque. As a rule, the maximum duration amounts to about just this thermal time constant. So it is 3.5 seconds. With these few slides, we have essentially given you the limits of a motor in terms of maximum speed and in terms of torque, continuous torque, and short-term torque. Now, how does current come into play? In reality, it is the motor current and not the torque that heats up the winding. However, torque and current are related, and the relation is very simple. There is a strict proportionality between the two, with the torque constant Km as the proportionality factor. For a given motor, current and torque are equivalent. So instead of a torque axis, we could have drawn also a current axis. Accordingly, the current at the origin of the nominal torque is called nominal current and can be found in line 6 of the motor data. The torque constant is given in line 12. It gives the amount of torque in millinewton meter produced for 1 amp of motor current. And now we can also understand what happens if the current is limited. Power supply or controllers have usually some current limitation. As we know now, this results in torque limitation. As a consequence, the continuous and short-term operating ranges might be restricted at the right. Load operation points that could easily be handled by the motor might not be achievable anymore due to the lack of current. So here is what you should have learned in this first chapter. First of all, motors have speed limits. They're based on bearing and brush life consideration. Second, motor torque and motor current are equivalent, and the relation between the two is given by the torque constant. Third of all, motors have torque limits. There is a continuous limit given by the nominal torque or the nominal current, and also short-term operation is limited. Essentially here, it's the time that limits short-term operation.